For decades, the story has been simple. Supersonic passenger flight failed because it was too expensive, too inefficient, too ahead of its time. Concorde burned too much fuel, tickets cost too much money, the economics didn't work. That explanation feels complete, but it isn't, because fuel inefficiency was only part of the story. The deeper barrier was not economic at first, it was atmospheric. To understand why supersonic airliners disappeared and why they have not returned, we need to look at something invisible: a wave. When an aircraft flies below the speed of sound, pressure disturbances move ahead of it. Air molecules have time to get out of the way. The atmosphere adjusts smoothly. But at Mach 1, that relationship changes. The aircraft begins moving faster than its own pressure signals can travel. The disturbances compress and stack, and instead of smooth pressure transitions, shockwaves form. These shockwaves merge into a distinctive pressure signature called an N wave, named for its shape when plotted over time: a rapid rise in pressure, a gradual drop, and a sudden return to normal. This is not just noise, it is a discontinuity in atmospheric pressure. Supersonic research documented this phenomenon extensively, demonstrating that the sonic boom experienced on the ground is the result of these coalescing shockwaves propagating through the atmosphere. And when that N wave reaches the surface, it does something economically devastating. It shakes buildings, it rattles windows, and, under certain conditions, it breaks glass. In the late 1960s, the United States conducted widespread sonic boom tests over Oklahoma City. Thousands of residents reported disturbances. Hundreds filed damage claims. Public opposition intensified. In 1973, the Federal Aviation Administration formally banned civilian supersonic flight over land in the United States, a restriction that remains in effect today. And similar restrictions were adopted elsewhere. At that moment, physics crossed into policy. Supersonic aircraft could fly, but not where most people lived, which meant they could not fly over continents, which meant they could not form global route networks. And this is where atmospheric physics became economic constraint. Airline economics depend on network density. Modern carriers survive because aircraft can be routed flexibly across continents. Planes connect cities in complex webs. Scale reduces cost. But once overland supersonic flight was prohibited, route geography collapsed. The Concorde could realistically operate only on transoceanic routes, most famously London to New York and Paris to New York. That dramatically reduced market size. Fewer routes mean fewer aircraft. Fewer aircraft mean higher unit costs. Higher unit costs mean expensive tickets. Economic analyses conducted after Concorde's retirement showed that its viability depended on niche premium markets, not scalable mass transport. The aircraft was not just burning fuel at high rates, it was trapped within regulatory geography. It was fast, but it was confined. And confinement is lethal to airline economics. Now, advocates argue that modern engineering can solve this. NASA's X-59 program aims to reshape the shockwave profile of supersonic aircraft, reducing ground boom intensity. Instead of a sharp N wave, engineers attempt to create a softened, low-boom pressure signature. Wind tunnel experiments and computational studies have shown that fuselage shaping can distribute pressure differently, potentially lowering peak overpressure. But here is the critical point. Low boom is not zero boom. Shockwaves are not a design error. They are a thermodynamic consequence of compressible flow at supersonic speeds. You can reshape them. You can reduce their intensity, but you cannot eliminate them entirely without slowing below Mach 1. And regulators must decide what level of disturbance is acceptable. Which means the problem is no longer just aerodynamic. It becomes societal. What level of atmospheric disruption is tolerable across populated regions? Until that threshold changes, the regulatory boundary remains. And if the regulatory boundary remains, so does the economic one. This reveals something deeper. Supersonic flight does not fail at the engine. It fails at the interface between physics and society. The barrier is not propulsion capability. Modern turbofan and ramjet technologies can achieve sustained supersonic cruise. The barrier is the propagation of pressure waves through a compressible atmosphere, interacting with human tolerance on the ground. This is a systems problem. The aircraft is only one node. The atmosphere is another. Regulation is another. Urban settlement patterns are another. Airline network economics are another. When those systems interact, the constraint emerges. Supersonic airliners are technically possible, but large-scale supersonic networks require permission from physics, regulation, and economics simultaneously. And those permissions have not aligned. So the real lesson is not about Concorde. It is about limits. Some technologies fail because parts break. Others fail because interactions exceed tolerance. Supersonic travel pushes against a boundary where atmospheric compression creates unavoidable ground effects. Those ground effects create regulation. That regulation reshapes economics. And that economic reshaping prevents scale. The speed barrier was broken in 1947. The sonic boom barrier remains. Not because engineers lack imagination, but because compressing air faster than sound transmits consequences far beyond the aircraft itself. And until those consequences are either accepted or fundamentally transformed, supersonic passenger flight will remain constrained, not by engine power, but by system boundaries. Speed was never the real obstacle. The wave was.